So this problem, which I forgot to hit the record button on, we will now re-talk. Sorry for all the people in the the audience at home watching on TV. So we got a spring, 24 centimeters long in relaxed position, gets stretched by 0.06 meters by this force, 300 newtons. This is the potential energy of a spring, kx squared. What have kx squared? I have to use the fact that Hooke's law could tell me what K is in terms of the force and stretch relationship. And so K becomes F over X, as we can see right here. And if you plug and chug all the numbers, we get down to 9 joules. Simple calculation. So now what we want to do is kind of put that number in perspective. If gravitational potential, which is mgh, and remember, this is really a work term because mg is the weight of something, its mass times gravity, and height is the length along which that force does work. So it's a force, we really have a force times distance. So your potential terms are all work terms. So don't be confused with they're synonymous, but they emphasize something different. The potential energy term is totally about what is the potential energy, based on position, whereas the work is specific about the force producing that particular displacement. There's two sides of the same coin when it comes down to it. So what is H going to be? Well, it's not hard to do this math. H would be, switch colors. H would be 9 joules. We'd just bring everything over. And the mass was going to be 80 kilograms. If we just use 10 newtons per kilogram in the bottom here, then we get something that's essentially whatever 9 over 800 is going to be. So the height will be 0.011 meters. Okay, so we're talking about a centimeter. So that spring, though it doesn't, 300 newtons isn't a lot of weight, okay? Divide it by 4, and that's how many pounds you're dealing with. All right, 75 pounds. So I guess that's, for some folks, it's a lot of weight. So the amount of energy that spring has stored could lift an average person. I'm assuming 80 kilograms is average. It might be above average. I don't know. It could lift that person a centimeter. Okay, so inevitably, as scientists and engineers, you'll have to have some feel for the work energy pieces of the puzzle that you need to do. And energy is the easiest way to find out these things because you don't have to mess with the vectors. All right, it's closer to arithmetic. All right, you may still have to tell the machine to do some calculus, but inevitably you're always trying to cheat the hard ways mathematically so that your code is as short and sweet as it can be. Just the faster that it computes, the less energy that it uses, the faster that it acts, et cetera, et cetera. So there's a lot of analysis that you'll learn in classes like this one and in similar foundational courses. And then when you get into engineering, you'll kind of repeat that drill, but then one of the goals will be, okay, we have this complex way of understanding it conceptually and mathematically. How would I tell the computer to do it simpler than the way I conceive of it? Especially if you end up working in, say, any application that has to do with space travel. Because you have a limited amount of energy to run code on sensor arrays, and so you want to find what's the fastest way to compute something and then make a decision about it. because you literally can burn up your battery or whatever your power source is. And so a lot of times they'll, these satellites or whatever that are out there, they'll do their thing for a while and then they'll float the solar sail and charge up, or there's a little nuclear reactor on board that still has limited lifespan. And so you're still wanting to make that thing last as long as it can. So you don't want sloppy code. So you'll need clean code and code that cheats the math well, without sacrificing the rigor of the math. Okay, so you learned a whole bunch of stuff in, say, your algebra course about simplifying stuff. You take some big ugly thing and whittle it down to a little thing. That's one basic kid level skill. Why do that? Well, besides getting through the math course, but where's that going to pay off? In what I just said. So, and there are more advanced tricks than that. But I digress. All right. New problem. A glass of beer. Wouldn't that be nice? Yeah, that's the problem with higher education. No beer and cigars in class. All right. 500-gram glass of beer slides along a level bar, and there's friction there. Kinetic friction, 0.1. So from a reading and translating standpoint, this coefficient of kinetic friction, that means that mu sub k equals 0.1. If you did any reading in the book, or if you read some of those additional problems that I uploaded from a self-published book that some fella did at University of Tennessee, forget his name, Murdoch or something, can't remember, where it had a bunch of examples, you would see this sort of thing a bunch, textbook and anywhere else. So its initial speed is 2 meters per second, so that means I could write that, and it comes to a stop, so I know the final speed is 0. All right, so we have those pieces of information, and we want to know how far. How far does it travel? So literally, if we use energy, which is the goal here, because we're talking about work, mechanical energy theorem here, we want to take the easy way out. And so let's take a swing at this. So we have our work kinetic energy theorem, and that just means in our case, well, we'll go ahead and write K minus K naught for those things. And the net work on this is also equal to, so all that kinetic energy gets eaten up by friction. And so we have simply, we would have friction times the normal force times the distance. That right there is essentially work equals force times distance. All right? And so the frictional force is this piece of the puzzle right here. All right? I'm sorry. I should say, I got a little ahead of myself. Let me, all you really want to do is erase that in for the moment, because I got a little ahead. It is the case that the force of friction is mu n, okay? Meaning the coefficient of friction times the normal force. And if you remember, the normal force took on at least 3 faces. It had the simple face when everything was just straight up and down. It was mass times gravity, which is what we're dealing with here. And then it had more complicated forms, whether or not it was on an inclined plane, whether or not there was a force applied at some angle to its motion, those sorts of things. This one's easy. We don't have to bother with all of that inclined plane business. So all of this works out to be that our network is going to be this force of friction, so mu in, and we could just put delta x is going to equal, if you remember, the final kinetic energy is 0. Okay, so we have a negative, and if I uh, uh, put in all the whatnot here, we have a minus 1/2 mv naught squared. Now, this is what we start working with. Okay, and so I have mu mg delta x is going to be a negative 1/2 mv naught squared. All right, so we want to know how far it goes. Solve for delta x, and we'll get a minus mv naught squared over mu mg. And nice that the masses drop out. So we get a negative v naught squared over mu g. So we do some plugging and chugging. We should have dropped a negative. What's that? Oh, yes, thank you. Got crazy with the dropping of things. And we should have had a negative persist in, oh, I'm sorry. When you do this, there's always a negative associated in the work kinetic energy theorem. So technically, we're going to have two negatives and they drop out. All right. So in our final analysis, delta x is just going to be that initial speed squared. So 2 meters per second squared over 2 times 0.1 times, if we just use 10 for G again on the test, I won't care which one you use. I'll be able to account for both on the test. And so all this works out pretty nice, especially if you use the 2 or the 10 rather. You get 200 centimeters or 0.2 meters out of this. Is what you'd calculate 0.2 meters directly and get 200 centimeters out of that. So makes sense. 200 centimeters, is basically going to be 2 meter sticks. I'm sorry. 200 centimeters. That's right. So it should be 2 meters. Let me double check that. So 4 over 2 is 2 over 1. Yeah, so yeah, 2 meters, which is the same as 200 centimeters. Whichever one floats your boat. Again, I wouldn't care on the test unless I specified give me it in meters. So this is just a relatively simple application of work kinetic energy. What was doing the work to eat up the kinetic energy would be a metaphorical way to put it. Friction does all the work. Now, I think I presented it in a way that you eventually should not need to do. If it's the case, something had speed and something caused that speed to go away. The only force in town is friction. That means that the work done by friction, so friction times length, has to equal half mv squared. And you wouldn't have to bother with negatives at all. So one way to, I guess, rethink this, we'll just kind of put it in its own little box here. If you say, all right, it had kinetic energy, That means it had 1/2 mv squared. And then friction made v go to 0. So that means that these have to be in balance, and 1/2 mv squared has to equal friction times distance. That's easier. Textbooks don't show it that way, so when you go and try to read it, it'll read like what I did first, which is correct. It is a way to approach it. But when it's a simple exchange, one force working to stop motion, if you satisfy that condition, did one force work to put an end to motion, then whatever that force is times the length that it did the work over has to equal the kinetic energy of the object. There's no other possibility. And so you could bypass all of the standard, write out the work energy theorem, go through all the ropes that your textbook will show you. You could just go straight to the answer. And of course, distance would end up being mv squared over 2 times the force of friction, or mv squared over 2 times mu mg, and you get the same thing. Okay? And you didn't have to worry about the negatives, dropping that or forgetting it, all that stuff. You could just think through it and just write what it has to equal what. It's the same thinking, it's conservation of energy. Right? So on a test question, if I ask this on a test, all I really need to see is what's in the blue box, and then you compute it to get the answer. If all you did was write what's in the blue box and plug it in and get an answer, I'd know you were thinking the right thinking. Or you simply memorized everything that you saw. That could be the other thing, all right? But the blue box is probably easily the most efficient way that is on screen right now. The other way is the way that it's traditionally exposited, okay? So I think that's one thing that gets in the way of, I guess, true learning, especially in courses like this one, is there's a lot of exposition that's touching every conceptual point because we're trying to instruct and change your thinking. But that's not necessarily the way that an expert would think it through every time. The expert's going to have shortcuts. How do you become an expert? Well, besides 10 or more years of reflective practice, you copy experts. And you try to go, okay, I understand what he just said. And if I detect the simplicity of one force doing work to stop motion, then I can easily apply that rule. Okay? So, all right, next problem. This one's kind of all theoretical. We're not going to get a number. We're going to get a formula. And this one exists really just to make a point about a particular feature of kinetic energy. So you're going at some speed, v. We're using capital V for speed. When you stomp on the brakes to miss a deer or whatever is there, and you're going to go some distance d before you come to a complete stop. If your speed had been twice that, what would the distance be? All right. So this is exactly what we just did. I have what force is bringing things to a stop here? Really friction that's bringing things to a stop here. So there's all this kinetic energy, 1/2 mass times big V squared, that goes away because there's the force of friction and some distance. Okay? So D, so the model, if you will, for distance in this case is just going to be basically what we saw a minute ago, mv squared over twice the force. We'll use little f for friction. Okay, it won't pay to bother with expanding friction into mu mg and all that jazz because we don't know what k the coefficient of friction is. None of that. Plus, we're not concerned with that. We're concerned with how is the distance related to the speed? That's what we're trying to work out here. So really, one way to look at this is if I just sort of get V by its, or just kind of separate out the factors here. So this is the general model. That's just the same energy exchange we just worked on and have worked on previously. So what if V equals 2V, then D equals what? Well, M over 2F isn't going to change. Just that's going to be what it is. But now I put a 2V in there. So really what this tells me here is that my D is directly proportional to V squared. It's really all it is saying. And so if I double my speed, I'm going to quadruple my distance. If I tripled the speed, I would factor of 9 the distance, the stopping distance. Okay, so you hear all that talk, when you're learning to drive, braking distances, you need a couple hundred feet at say 65 miles an hour to come to a full stop. Doesn't seem like it when you're on the road though, mainly because everybody's slowing down at roughly the same pace. But that's why you don't want to tailgate, because if somebody comes to a more abrupt stop than your brakes normally provide, like they run into something, well, then you're going to run into them too. All right, so that's why that count to 2, keep your distance. Almost nobody does it. It's okay if they do it in the right lane, but when they do that in the left lane, that makes everybody mad, Go, speed up, jerk. All right. So basically we get 4D out of that if we do that. So the basic idea here is the speed business has that squaring factor of the kind of distance that it's going to take to do things. So a lot more work, a lot more heating due to friction in this case. And so the more times you do this sort of thing, the harder it is on your tires and your brakes and blah, 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 blah. Right? So just a kind of more of a conceptual example than anything. All right. Box on an icy sidewalk. So here's a box, a pretty green box with yellow sides, sitting on an icy surface. If it's icy, we get to assume no friction. Effectively no friction. Technically not true, but why not? We'll make our lives a little bit easier to do this. Then a spring with an 88 Newton per meter spring is attached to that box. All right, so that's a perfect spring. All right, it's been sprung a few times, looks like. K is 88 newtons per meter. How much does the spring stretch if we accelerate the box at 2 meters per second? So since I bring up acceleration, what if the spring is being pulled and there's no friction? How many forces do I have? 1, right? What does Newton's second law say about the sum of forces? Has to be equal to sum of forces always equals, what's that? No. If acceleration is 0, it equals 0. Otherwise, symbolically, sum of forces always equals Newton's second law, ma. All right. So this one is sort of a little bit of a trick. Sum of forces equals ma. Well, there's only one force, and the force that we're dealing with here is kx. That's Hooke's law. That's the only force that we're dealing with. If there was some friction, then it would be kx minus friction. That would be the sum of forces. This has to equal ma. So kind of simple, actually. We know the k, we know what mass and acceleration are. We want to know what the stretch is. How much is the spring stretch? So x equals ma over k. So 22 kilograms, 2 meters per second squared over the 88 newtons per meter. And we get a half meter. That's a big stretch. Half a meter stick. That's a Newton. Yep. So this would be 44 newtons over 88 newtons per meter. Yeah. Hence the half a meter. So a simple one thrown in there. All right. So don't lose sight of the fact that sometimes it's just a force balance. All right. So there we go. Next problem. Snowboarder. So let's draw a picture of the snowboarder. So there's a quarter pipe, all right, and so the radius of this quarter pipe is 2 meters, all right. So just a curved slope for some snowboarding. And let's say that we have I didn't give the mass of this snowboarder. Let's just say this snowboarder has, I don't know, let's make it easy. This is a really small snowboarder, okay, 10 kilograms. It's a raccoon, all right? Who knows what it is? It's a raccoon from Avengers. Okay, what's his name? Rocket, yeah. Can remember. So Rocket is snowboarding, all right? And if Rocket's up here, I'm not going to draw a raccoon, all right? Here's Rocket, okay? Rocket slips over the edge there, inevitably will slide down to the bottom of the quarter pipe. And so what's the speed at the bottom of the quarter pipe if they just kind of roll over the edge there and let gravity do the work? So here's a thing to know, I guess. So far, we've talked about work equals kinetic energy, change in kinetic energy. And there's a thing called mechanical energy, which is the sum of potential and kinetic energies going into a situation equaling the sum of potential and kinetic energies coming out of a situation, okay, when everything's conserved. So there's this mechanical energy idea, and it's nothing new other than we're calling the particular connection of potential energy initial plus kinetic energy initial equals potential energy final plus kinetic energy final, okay? Or in this case, potential energy would be a potential energy due to gravity initially, all right? So we'll have an mgr, that's our h, that's how far vertically gravity is doing work even though the path is curved, So our h in this case is equal to r. We've been using mgh for strictly falling, all right? But in this case, the snowboarder's falling a height of r, but through a curved path. It doesn't matter for the energy. Energy could care less about the path, okay? So mgr plus half mv naught squared, it's going to equal mgr at the bottom plus half mv squared at the bottom. Well, initially, there's no speed, okay, initially, at least in the direction that things are happening. And then at the end, there's no radius. There's no potential height associated with the potential energy. So it's, again, this is a simple connection between gravitational potential. We could literally say gravity equals kinetic. So I write this again to bring up what I said earlier. One could start with, all right, here's the mechanical energy definition. I'm going to list everything. I'm going to cross out all the zeros and have what I have. That's an effective way to go. And if you have more than one exchange, then that's effective. And I've showed other examples, like the friction energy thing that you had the handout to work on. That was a bit more, you had to pay attention to more things. This one is another easy one. If all it is all this gravitational potential went to speed at the bottom, then you just write gravitational potential, mgh, the mass gravity times height, in whatever way you're measuring height, has to equal half mv squared. It's the same as if I drop this. It has some sort of potential based on its mass and how high it is above the ground. And right before it hits the thing, the ground, it'll have some speed that's associated with its kinetic energy. It's one exchange. So same things here, just it's an exchange over a curved path that we're assuming is frictionless because it's snowy, icy. All right. So again, we just have mgr is going to equal half mv squared. We wanted to know the speed at the bottom. So the speed at the bottom is just going to be, well, let's remember the masses cancel, all right? And so the speed is just going to be 2gr, square root of 2gr. So that means 2 times 10 meters per second squared times, what is it, 2 meters. And so the speed in this case will be whatever 2 root 10 is, all right? Be 2 root 10 meters per second. And I would inevitably, actually, I wouldn't care if you resolve root 10 or not. At this point, I know that you are capable of computing a square root of 10 on your calculator. So if you leave it as an exact number, because currently 2 root 10 is an exact number, it's as soon as you do the square root, that's when it becomes less precise, less accurate, okay, because of the irrational number. So that's a perfectly good answer, 2 root 10. If you just got to know, then run it out to some number of decimals, couple decimals, and you'll be set. So that's a simple one. And that really the point here is if we had just dropped something from 2 meters, is it 2 meters? Yeah. And it was 10 kilograms, we'd get the same speed at impact. So I suspect that Disney, as in Disneyland, employs at least a few engineers. And every now and then they do roller coaster design. And roller coasters have curved paths, and we get you up to a height, and then we let it rip. Guess what they're doing? A more complicated version of this. In fact, I think in the Energy Skate Park lab, I wanted you to mess with the loop-de-loop, and you see that basically it's still that's still about the energy exchange, potential to kinetic, gravitational potential to kinetic. So same basic idea, just gets a little bit more complicated. You know, if this um, roller coaster, the roller coaster has a constant mass, and then on average, what would you expect the mass of the riders to be? That's not hard to do. You can, you know, what's the average mass of a person in the United States? And you could just say, all right, I have 20 slots to fill. The average weight is this. Guess what? You're going to be pretty much on target. And if you just say, all right, I'm going to design this with a fudge factor that accounts for it, or you put real sensors into the system, and every time a new group gets in, it goes, all right, here's the mass. That means the speed needs to be 1 meter per second faster or slower when we start so that the rest of it works out, so that the experience is the same each time. Okay? That would be a way to go. I don't know if they do it that way now because I didn't look it up, because I didn't think of it until just now. So, all right. But there's always that somebody's thinking that through, and then I guarantee you at least one engineer is employed at Disneyland, you know, to design and field test these sorts of things. One more problem. Frictionless air track. So let's draw us a frictionless air track that matches this problem. So here's an air track with some things on the end. Here's a spring, and here's a spring. All right. And we're going to bring a box into this mix here. So there's our box. And this box is going to smash the left spring. So if it's a spring, then it has a spring constant. We'll call this one K sub L for left. And the right spring would have a K sub R. And the glider has some mass M. So what's the max compression of this spring, of the right spring? Because we're going to smash it by some length X. So there'll be a there was some smashing of that spring. Otherwise, it's not going to slide on this air track. And so again, it's air track, so we're going to assume it's frictionless. All right. Mu equals 0, basic assumption. All right. So again, what do we have? We want to, what is the max compression on the right spring? So what's going to be true initially about the kinetic energy when all I've done is compress the spring? Is it moving? Nope. Kinetic energy initially is 0. It slides across, has some kinetic energy in the middle. At max compression of the spring, what's the speed? So the initial and final kinetic energies are 0. All right. So we could say, you know, to encode that, we could say, well, initial kinetic energy equals final kinetic energy equals 0. In fact, I'm going to rewrite that because we're dealing with spring constants that are K, so let's not be kinetic energy initial equals the kinetic energy final, which is going to be 0. So literally I have whatever spring potential is in the left spring ends up getting gobbled up by the right spring. So here I have a transfer of potentials based on the way the problem stated, because we ignored what happens in the middle. All right. the way that this question was asked. So quite literally, the initial spring potential is going to equal the final spring potential. This one goes to that one. So you literally just have 1/2 k left x squared equals 1/2 k right x squared. Actually, I need to make sure that I put the stretch designators on too. That would be an easy way to get this problem goofed up. Because you have a stretch on the left and a stretch on the right. Okay? Now, if they're the same spring constant, then you'd have one stretch. But we don't know that. All we know is we have two springs. And so if they're different spring constants, then we definitely need to encode for different stretches. And if they are the same spring, then it still won't matter. We'll still have encoded for both stretches, even though they'd end up being the same, all right, with no friction. And so the halves drop out. And we want to know max compression on the right spring, so we solve for that. That means my XR is going to be equal to KL XL squared over KR, which means I'm just going to have, when I do the square root of all that, let me take this, I need to be careful, I had it squared there. So when I take the square root of all this jazz, then I'm going to have XR, and we can pretty much ignore the negative, right? Because we're just worried about the magnitude. So the XL squared pops out as just a single XL, and the other stuff has to stay underneath. So I'll have XL times the square root of left over right spring constants. So this right here this is the kind of thing that would get encoded into a control system for some process that involved this sort of thing, all right? And you might even connect this to maybe something pushing. If it says, all right, when some box came out of the chute that was bigger than the last one, it smashed my first spring, okay? And so now this other spring, is it going to be enough? So if you always know, the only kinds of boxes coming out of the chute are this range of masses, therefore when it bounces on this spring, it'll slide down and bounce on that spring and everything works all the time. If that's fine, you don't have to worry about it, who cares? But somebody had to do this math to pick the right spring. All right? Or they had to do this math because if it's this size box, it's going to go down this chute. If it's this size box, it's going to go down the other chute. But we're going to push it out the same no matter what. One spring pushes it out. And if the box is this big, it's going to, and it could be a size thing. Box is this big, we'll go through that one. If it's this big, it's not going to go. It's going to push off there, different spring over there. So that when it gets to the bottom, it bounces and goes on the conveyor belt or whatever it is. So I do this. Some of these problems are find the value, and some of these problems are make the model. Because as engineers and scientists, you're going to work with a model before you compute anything. This model has to go into the code of the control system. Somebody's doing that, period. Or you're going to come in and edit what existed because there was a redesign. And you'll have to go, yes, this still works for us. Or no, we need to tweak this in some way because the parameters have changed. Yep.